Assalamualaikum and a very good morning. Okay, this is chapter 3, okay, for our lesson today, which is polymerization reaction techniques. So this chapter will cover your test 3, which is final exam test. Okay, this is some polymerizability of vinyl monomer. Okay, tak payah tengok lah yang ni, kita skip. Alright, we look at the thermodynamic of polymerization. Okay, thermodynamic of polymer solution are determined by the interaction between the solvent and the dissolved substance, which is called as the solvent quality. So this chapter we will discuss about the process or some techniques to produce polymer. So we have several polymerization, which is suspension, emulsion, and so on. And to understand the thermodynamic of polymer solution, we use the Gibbs law. Okay, Gibbs-Helmholtz equation or Gibbs law given by delta G equal to delta H minus T delta Sp. So delta Gp means that the Gibbs free energy during the polymerization, and delta H is the enthalpy of polymerization. T is the absolute temperature, delta S is the entropy or change in the entropy, and P is the polymerization, which is at the respective values in the mixture. So when the enthalpy of polymerization is less than 0, dia punya bond dia from sigma bond change to sigma kan ni, pi bond change to sigma bond. Okay, dia punya conformation, okay, which is the rotation of the bond from pi bond to sigma bond. When the entropy, delta entropy or the change in the entropy is less than 0, loss of transitional entropy happens. So polymerization favored below a ceiling temperature, which is Tc equal to delta H over delta S. Okay. Some example of the value for enthalpy, entropy, and ceiling temperature. Okay, we look at the reaction rate constant given by K. So what is the reaction rate constant? Okay. So the reaction rate constant is actually a proportional factor in the rate law of chemical kinetics that relates the molar concentration of reactant to reaction rates. So it is also known as the reaction rate constant or reaction rate coefficient and is indicated in equation by the letter K. And the rate of disappearance of A, which is the species A ataupun polymer A, depend on temperature and composition, and it given by negative RA. And the rate law gives the relationship between reaction rate and the concentration. Okay, relation between the reaction rate, which is negative RA, reaction rate constant K, and concentration of various species is given by this formula. So the algebraic equation that relates negative RA to the species concentration is called the kinetic expression or rate law. So the reaction rate constant K is not truly a constant, but it is independent of concentration of the species involved in the reaction. So basically, the question will ask you the meaning of negative RA and RA. Okay, these types of answer. Okay, example of the question like state in words the meaning of negative RA and RA in terms of the polymer reaction system. So you have to give this answer. Okay. So RA is the rate of formation of the species A per unit mass of catalyst. The rate law is an expression for the reaction rate in terms of concentration of chemical species involved in the reaction. For example, we have monomer A plus the monomer B, and we will produce a yield which is C, whereby the K is the rate constant, alpha is the reaction order with respect to A, and beta is the reaction order with respect to B. And alpha plus beta is the overall reaction order. And the rate constant is independent of the concentration of the chemical species involved in the reaction. However, it depends on other factors such as temperature or ionic strength. So the units of the rate constant depend on the overall reaction order or vary with the order of the reaction. Concentration is usually measured in m for solution reaction and in molecule for gas phase reaction. Okay, so in the polymerization reaction, okay, we have two techniques which are homogeneous and heterogeneous. In homogeneous system, it is categorized under bulk and solution. Okay, bulk and solution is categorized under homogeneous reaction system, and heterogeneous is consists of suspension and emulsion polymerization. So all the polymerization system, which is the step to produce polymer process. This is example of the polymerization process, which is held in the reaction flask. Okay, we call it as the reaction flask, complete with the thermometer, nitrogen in, which is the nitrogen insertion of the nitrogen gas. Also with the agitation, this is the agitation, and run at certain temperature. Okay, this schematic diagram use a hot plate and use a water as a medium. If we look at the bulk polymerization in homogeneous system, okay, for bulk polymerization, it is suitable for free radical and some step polymerization. Okay, it produces the highest purity, and it needs a monomer soluble initiator, which is initiator that can be soluble in the monomer, and also the chain transfer agent. For example, styrene for polystyrene and ethylene for LDPE. Two types of polymer and monomer condition for bulk polymerization, which are the polymer is soluble in the monomer, and second one, the polymer is not soluble in the monomer. Okay, polymer is soluble in monomer means that viscosity of the reaction increase, which is will give the gel effect. So we will look at what is gel effect. And the polymer is not soluble in the monomer means that polymer will be precipitate without increases in solution viscosity. Please describe this situation is situation for gel effect. Okay, actually the choice of the methods to produce polymer, whether the bulk, solution, emulsion, it is actually depend on the monomer and the resulting polymer, and also the condition, which is temperature and pressure. In bulk polymerization, the system, which is the polymerization by opening the C double bond C, is exothermal process. So polymerization in substance, which is bulk, it involves substantial challenge to remove the heat generated. So moreover, viscosity problem arise, which are caused by increasing the viscosity by multiple order, which is transition of a liquid to a solid. And the local overheating is possible as a result of the gel effect. Okay, so the other names for gel effect is Transderm's effect. And in this case, the molar mass distribution of the product can change, or the polymer become discolored as a result of oxidation or decomposition. So One solution is to interrupt the polymerization at conversion of 40 to 60% and recycling the residual monomer. So we have to avoid gel effect. Okay. This is the advantages of bulk polymerization. It is simple, which is only involve monomer, initiator, and chain transfer agent, and produce high yield per reactor volume with high purity, easy polymer recovery, option of casting the polymerization mixture into final product. So this method reduces the heat transfer problem. Some disadvantages, okay, difficult to remove the last traces of monomer, polymer to dissipating heat produced during the polymerization, especially in the radical polymerization, is highly exothermic. Difficult to remove heat near the end of polymerization when viscosity is high. Okay, when you cannot control the viscosity at the end of the reaction, it is very hard to remove or to slow down the temperature. High viscosity limits the diffusion of long chain radical as required for termination. High radical concentration will produce high rate of polymerization. Compared to the propagation side, the diffusion of small monomer molecule is less restricted, which is RT decreases rapidly, then RP and R not increases due to the increasing of heats. And heat dissipation can be improved by providing special baffle to improve heat transfer. Okay, you can refer notes, check the chain polymerization. Saya ada letak equation apa, what is the relationship between RT, RP and RO. Okay. We'll look at the solution polymerization. Before I forget, the example of polymer produced by bulk polymerization is polystyrene and PMMA. Okay, look at the solution polymerization. The solution polymerization is not significantly different to polymerization in bulk. So the same kinetic laws apply. So in both polymerization methods, which is bulk and solution, there are problems with viscosity and temperature control. Okay, at higher conversion. So although both problems are ameliorated by the added solvent, formally, bulk polymerization can also be described as solution polymerization, where the monomer is the solvent for the polymer rather than another. So solution polymerization is a typical laboratory method. Industrially, it is used more for elastomer polymerization, for example, in the production of polybutadiene, EPDM, and for for special SBS graded. Okay, so it is rarely used for thermoplastic. So it is often employed if the polymers is to be marketed as a polymer solution, such as in often the case with functional water-soluble polymer. So in some cases, the polymer is not or is only slightly soluble in its own monomer. So that with increasing conversion, the polymer will be precipitate. So it uses the organic solvent or water, and initiator and monomer must be soluble in the solvent. The solvent characteristics are acceptable chain transfer agent, suitable to melting and boiling points for the polymerization condition, can easy removal, influenced by flash point, cost and toxicity. Example of the solvent used are aliphatic and aromatic hydrocarbon, ester, ether, alcohol. So in most cases, the reason for the limited solubility is that the polymers are crystalline or semi-crystalline. And then the kinetics are not different to those in solution.